we'll just also like make sure the audio is captured.
Yeah. I'll test that.
Then afterwards should be fine.
Okay. Check the stream.
Is it live right now?
Yeah, it's live.
Are they presenting? Oh wait, this is web. Wait, so are they also going to be presenting the MathSoc channel as well? Like Brendan, Thomas?
They're on there. They're doing different ones.
Okay, yeah.
Cool.
Let me just listen a bit. Presenting exactly. Wait, so today we're going to be presenting.
Unless it's here. I'll turn that mic up. Limit that mic. I'm not muted.
Listen a bit.
That's muted.
Wait, is it echoing because it's picking up audio? I'll mute this stream for a sec. And we'll just like chat for a bit. This audio wasn't playing in. And then we'll change.
Yeah.
No, it's
Still echoing. Is that normally happen? I normally don't score something more million.
Oh wait, is it because we need a deafen one of us as well? Is that why?
So I'm muted on this.
Yeah, but if one of us is deaf, it'll pick up the audio, right? Something like that.
Okay. How do you do that?
Wait, you can't mute and deafen, right? Why deafen? But you can't deafen without mute. It's too hard to think about properly. Only problem is echo now. So you're muted, which means it should only pick up the audio once. Why is it echoing?
Apparently speakers like a bit.
Yeah.
Are you on speakers?
Like what do you mean?
You got some phones or something? Connect. Try that. No, it's just searching up here. It says when your microphone sounds up the sound, you speakers because feedback loop result and echo.
Yeah, that's why I stopped the thing and it's still echo.
Okay. Even when you got headphones, you use on that.
No, I didn't bring it.
You bring it?
We can check what we just said.
Exactly.
I wasn't playing it.
Where your audio settings on? What about you? What's your audio settings?
I mean, it's just it's not muted, not deafened.
Like, but what's no.
Audio output.
Why does it say max out? It's because
Oh, is it because of that?
I'm gonna try it. It's
because it's picking that thing as well. There's no way.
On devices, iPad. I think it should be exclusive your iPad. Okay, it's been removed.
Okay.
Oh, we did it, mate.
So it's just because it was picking up the audio from that thing.
Okay, well, live stream has.
Okay.
Yeah. Live stream started, so.
Let me know if there's any other issues.
I will.
I'll do the live stream.
I'll listen.
Alright.
We're good to go then, yeah?
We're good to go.
Right. Little apologies for the late start.
Gotta switch up. Discord.
Yeah. Okay. Anyways,
Apologies for the late start, guys.
Ran into a few
Tech issues here and there.
But you know, it always happens. Okay. So, what are we doing? 2901 seminar part 2. Get hyped, guys. Okay, let's take a look at the content overview real quick. So what we're gonna have the convergence of random variables, estimators and their properties, parameter estimation inference, and then hypothesis testing at the end. Okay. Let's get right into it since we are a bit late. Convergence of random variables, right? So to kind of understand convergence of random variables, let's have a think. What are the different types of convergences?
So
I thought it was fine. Okay. What's the trick? Convergence of random variables, right? So to understand
Still echo on this.
Wait, did you mute yourself? Are you muted?
Yeah,
you are.
Yeah, I'm muted. Yeah. So I removed you from there.
What if I mute and then you unmute? Try that then.
I'm trying. I'm trying that now.
Yeah, see if this works. Well, what is it? What?
Just waiting.
What if I mute and then you unmute? Try that.
I'm trying.
But why is it always fine when you speak?
I'm trying.
Yeah, see if this works. Well, what is it?
I mean, it's working when. Hello? Testing?
But why is it always fine when you speak? Yeah, see if this works. Well, what is it?
I mean, it's working. Testing?
Hello?
Testing?
But why is it always fine when you speak?
I mean, it's picking up well for me. Just really speak clearly and see if it's fine. Now, try it. Just speak really clearly, I guess.
Okay, let me know if there's any problem.
Yeah, I'm going to listen to it. Just let me know.
Okay, anyways. So, is it fine? Oh, what? I feel like it's playing the same audio twice. There's a bit of a delay, but it's playing the same audio twice as you want.
really speak clearly can see like it's fine. Now, try it. So speak really clearly. Yeah. Try and speak.
Okay.
Yeah. Is that
sure.
alright? Try that.
All right. Okay. So convergence of random variables. What we're gonna say, two different types of kind of convergence you can define here. There's the convergence in distribution and the convergence in probability, right? In the question here, we aim to show that these both converge to 1. Okay. So then, how might we go about solving this question? Well, we might want to refer to the definition of convergence, right? We say that sequence of random variables converges in distribution to a random variable x if the limit as n tends to infinity of fxnx is equal to fxx for every x. And yeah, as we've seen, this means that xn approaches in distribution to x. And that's exactly what we're trying to show in the question, right? xn approaches in distribution to 1. Okay? Let's have a look at how we might solve this question, right? So, as always, we integrate to find the cumulative distribution function, remembering that from the previous formula, we were dealing with the CDF. So, we integrate, find the CDF, find that it's equal to x to the 2n, right? What happens when n approaches to infinity? Well, since x is a value that takes a value between 0 and 1, it's quite obvious that it'll be 0 in any case, right? You take a value that's smaller than 1 and you keep taking it to higher powers, it's going to get smaller and smaller. So that's why it goes to 0, right? Okay, so if it goes to 0, what does this mean? Well, my CDF is going to be equal to 0 at every single point except when x is larger than or equal to 1. In particular, when it's equal to 1, it should have value 1, right? And what does this mean? This has a distribution of 1, right? The CDF will have a distribution of 1 when x is larger than or equal to 1 and 0 otherwise. So that's why it converges in distribution to the distribution of 1. Okay, next part is about the... okay, yeah, so this is just order working out, but next part, we have to show that it converges in probability. So it's kind of a different definition, and I think we'll find out later, like, you know, what's the kind of relationship between them. Well, how do we show that something converges in probability to another variable? Well, we'll take a look at the definition once again, right? What does the definition say? If I want to say some variable xn converges to a random variable x, then the limit as n goes to infinity of the probability of the difference between the two variables, or the absolute value of the difference between the two variables, should be larger than epsilon. Well, the probability of that happening is equal to 0 for all epsilon larger than 0, right? So what does this kind of remind you of? Kind of reminds you of like the limit argument in a way, right? You choose any epsilon, no matter how small it is, and the difference between them, the probability of there being a difference between them is still going to be equal to 0, which is essentially saying as n approaches to infinity, xn approaches in probability to x. Okay, so how might we do that for this question? Show that xn approaches in probability to 1. Well, you want to set up the equation, right? Probability that, absolute value of xn minus 1 larger than epsilon is equal to 0 for all epsilon larger than 0, right? This is what you are trying to prove, right? How can we prove that? Well, kind of idea here is you want to be able to split up your absolute value into two kind of sections, right? And we'll see that happening in a sec, right? So yeah, we've computed what the limit that we should try and prove is equal to 0. We split it up into the two kind of cases. So basically we just remove the absolute value brackets and split it into these two cases. So either it is xn minus 1 larger than epsilon, or xn minus 1 is less than negative of epsilon, right? Those are the kind of two possible cases we have, right? Now, just for simple rearranging, we get either xn is larger than 1 plus epsilon or xn is less than 1 minus epsilon, right? And you can see that these two cases are kind of like mutually exclusive, right? You can't have it being larger than 1 plus epsilon and less than 1 minus epsilon at the same time if epsilon is a positive number, right? So we can essentially just add the two probabilities together, right? Now, there's something to notice here, right? What is the probability of xn being larger than 1 plus another number? Well, that's 0, right? Because if you see how we've defined the distribution, it's only valid for x's between 0 and 1. We'll have probability 0 everywhere else, right? So we know that at least that part evaluates to 0. And now we kind of need to show that the probability of xn being less than 1 minus epsilon is also 0, right? How can we do that? Well, if you kind of notice, this looks exactly like the format of the, the CDF, right? So essentially all we have to do here is we just substitute this into the CDF, which we've already found, right? As we see here, the CDF is equal to x to the 2n, sub 1 minus epsilon in here. What do we get? 1 minus epsilon to the power of 2n as n goes to infinity. 1 minus epsilon is going to be a quantity less than 1, so we know that that's going to go to 0, right? Well, actually, to be fair, in this case, we only dealt with when epsilon is between 0 and 1, but it's kind of irrelevant for cases when epsilon is larger than 1 anyways, right? Yeah, because if epsilon's out of the range, 1 minus epsilon would not even be a possible x value, so the probability would be 0 in that case as well, right? Remember, x is between 0 and 1. Okay, that's a little bit of recap on that stuff. Next thing, almost sure convergence, right? Sequence of random variables x1, x2 converges almost surely to a random variable x if the limit as n approaches to infinity of xn equal to x is equal to 1, right? So basically, if you take all of these random variables, right, you take the limit as n approaches to infinity, I expect that it should be equal to x, right? Probability equal to 1 is I'm basically very, very sure that it will be equal to x. And that's the notation a dot s, right? Almost sure. Okay, now convergence in L to the power of p. So kind of like the same idea as before, but we're just raising to different powers, right? If we say that it converges in L to the p, all that really is saying is that the expected value of the power of the differences, or like the absolute value of the difference, is going to be equal to 0, right? What does that really mean? Well, we're going to look at it soon. Okay, so we have comparison of convergence strengths, right? And this is what I was talking about before by like the relationship between the convergence in probability and convergence in distribution, right? What's the kind of relationship? Well, first of all, almost sure convergence is kind of like the strongest form, right? Almost sure convergence implies convergence in probability, which implies convergence in distribution, right? And you can see that's the same case for when we take convergence in L to the power of p, right? And also we know that it's stronger for higher p, right? So for example, p is equal to 2 would imply p is equal to 1 is true, p is equal to 3 would imply p is equal to 2 and 1 is true, and so on, right? Okay, now we're moving on to the central limit theorem, which I hope and I'm sure most of you are already quite familiar with. So why does central limit theorem kind of work, right? It's just the idea that most things in life, if you take a large enough sample size, everything tends to be normally distributed, so we can approximate them using the normal distribution over a large enough sample size, right? And typically you want them to be IID in order for this to occur as well, right? So for example, if we know that these 48 different kind of variable, like IID variables are uniform random variables, we might want to, look at the sample mean, right? And calculate the probability that the sample mean is larger than 0.55. Obviously, without using the central limit theorem, this becomes quite tedious, right? There's just a lot of cases to deal with. You have 48 different variables, right? But with the central limit theorem, like obviously it's just an approximation, but it gets better and better as the larger the number goes, right? That's pretty much all what we've been saying in this course. Okay, so here's just the definition of the central limit theorem. I think the most common one is the one you see at the bottom. So your sample mean minus your true mean, I guess, divided by the standard deviation should converge in distribution to the standard normal distribution, right? Okay, so how might we use that for this question? Well, have a look. For this uniform random variable, right, if you refer to the distribution table, you'll know that you'll have these parameters as your, mean and standard deviation, variance, whatever, right? So we'll just go compute them, right? Mu equals to half, sigma squared equals to 1 on 12. But then remembering for when we deal with sample mean, the variance is not the same as the variance before, right? So the variance of a single variable is obviously not going to be the same as the variance of like 48 variables added together and divided by the number of variables, right? Why is that the case? Because averaging stuff out tends to reduce the variability, and that's why variance is decreased, right? And the factor that we decrease it by is dividing it by n, right? So in this case, the standard deviation, you divide by square root n, right? Okay, so if you want the probability of your sample mean to be larger than 0.55, essentially what we want to do is it's hard for us to make a distribution for every single different type of normal distribution, right? But what we can always do is we can just make a standard distribution for the standard normal distribution, and we can always go back and convert everything back to the standard normal distribution, right? And that's exactly what we're trying to do here, right? So we're essentially trying to make our probability, we're rearranging it, we're minusing the mean, dividing by standard deviation. And what's the point of that? So we can get it in terms of a z-score, and we know that the z-score is modeled by the standard normal distribution, which we typically will have values for, or like a table, or like some type of values to help assist you and guide you as to what the probability should be, right? And we'll figure out that in this case, the probability of z being larger than or equal to 1.2 will be equal to 0.1150697. In the exam, I think something they might give you might be something like, you'll see like this function pop up a lot, of 1.2 will probably equal to 0.885 or something like that. Yeah, I think 0.885. And then you'll know that so this will give you the probability of z being less than or equal to 1.2. So that's what this function kind of corresponds to, right? And then so you know that if you want larger than or equal to 1.2, then you just do 1 minus, right? Okay, now onto the law of large numbers. So there's kind of 2 laws of large numbers that we learn in this course. The weak law, first of all, which is saying if we have some sequence of independent random variables, same mean, finite variance, then the sample mean would converge in probability to the true mean, right? In a way, this kind of makes a lot of sense, right? If you take large enough sample size, you'd expect that if you keep computing the mean over and over again, as you take larger and larger sample size, eventually you'll get fairly close, right? And in this case, we're saying we're gonna go probably like to infinity, right? So that's why we say it converges in probability to the true mean. And then strong law of large numbers is the same, but as you might expect, it would be stricter, right? So the convergence happens almost surely, right? As per the definition before. Okay. Yeah. Just a quick summary. As you take larger samples, sample mean approaches the true mean. Okay, and then why is the central limit theorem, why is it kind of useful? Well, most of the distributions we've been learning throughout the course, we can actually model using the central limit theorem, right? If you're interested, you can go have a look, but as I'm pretty sure we've seen, most models do tend to follow the central or like the normal, like normally distributed over a large enough sample size. Even though some models, because they are like asymmetric or whatever, they might take a much larger sample size than others. But generally speaking, the binomial distribution is fairly symmetrical, so it will tend to the normal distribution a lot faster than all your other models. But this is a particular case, right? So you have some variable x, which is modeled by the binomial distribution, and you want to normally approximate this thing. How can we do that? Well, you need to figure out two pieces of information, right? What is the mean of this random variable, and what is the standard deviation, right? And you can read all of this information off the distribution table, but it will be NP, and which is the mean, and then the variance should be NP1 minus P. So then this standard deviation will just follow as the square root of the variance, right? And then you think about, how do I normally approximate a variable? Well, you minus the mean divided by the square root of the variance. And then, yeah, as you'll see, and then obviously that's just the case where we're not even considering the sample mean, right? But maybe if you want to consider the sample mean, remember we have to divide by the scaling factor of square root n. Okay. And then, yeah, this is just a quick slide on continuity correction. Why is it kind of relevant? Or like, it's, I guess, not too relevant for this course, but you can give it a search if it's relevant, if you're interested, but it's not too relevant to us. Okay, applications of the central limit theorem. So, this is a question taken from the 2020 MATH2901 paper. It's actually question 1II. You have two theaters that want to compete for the business of 1,000 customers, and you assume each customer chooses between the theaters independently, right? And they are indifferent between the two. Let n be the number of seats in each theater. Using a binomial model, find a condition in terms of n, which will guarantee that the probability of a particular theater turning away a customer is less than 1%. Okay, so the first step might be to figure out what exactly the parameters of your binomial model are, right? You have 1,000 customers, so that's like n equals to 1,000, and you're told that they are indifferent between the two. So what does that kind of suggest to you? The probability of choosing either should be the exact same, so we should have a probability half in this case, right? Now we know that what kind of model we're gonna, like, we know the model, we know the parameters of the model, we can go ahead and try to figure out the probability of it being less than 1%, right? Okay, so yeah, how do we write this? Well, we don't know how many, like, what do you call it? What's this thing called? Yeah, we don't know how many seats we should have, right? So we let n be this kind of number of seats. And to find this n, we need the probability of x being larger than n to be less than 0.01, right? Because whenever x is larger than n, that means we have too many people, right? The amount of people represented by x is larger than the amount of seats we have, which is n, right? And we want the probability of that to be less than 0.01. Okay, so if we try to compute like an actual equation to figure out using the binomial model, you'll see that it becomes this very is it complicated? It's not exactly a complicated expression, but just a very long expression that's going to become very hard to solve, right? Like, I look at this and I don't think I really want to solve it. I don't think you really want to find what the value of n is here. Maybe you can guess and check a couple times, but definitely not ideal, right? So, yeah, exactly as you can see, right? Solving for that n in the above expression is not easy, so why do we want to take a different approach? Let's see what part B asks. Explain how the binomial distribution can be approximated by a normal distribution, right? Okay, so let's have a look. So we have the distribution, which means we can find out the mean and the standard deviation, right? If we have the mean and the standard deviation, we also can apply the central limit theorem, which is to say, for large enough n, we can apply central limit theorem and say that it converges to standard normal distribution, right? Well, in this case, as we've seen from before, we know that it should be x minus np over square root np times 1 minus p, which converges in distribution to standard normal. Okay, so if we want the probability of x being larger than n to be less than 0.01, what does this mean? Well, then we have to minus the mean from both sides, divide by the standard deviation, right? And you know that your random variable x minus the mean divided by standard deviation, that's just going to be kind of like your z-score, right? So what do I kind of need now? I just need my z-score to be larger than n minus 500 over square root 250 to be less than 0.01, right? Or like the probability of that happening to be less than 0.01. Okay, so how can I solve this? Well, this is kind of like a little bit of reverse engineering, right? You look at the kind of table and find out which z-score gives you a value such that the probability of it happening is 0.01, right? You find the z-score that corresponds to that. So in this question, you're given the following information, right? How do you kind of interpret this information? Well, what does this kind of say? So imagine you have like it's not the best bell curve, but I think we can deal with it. Let's say the value 2.32 lies about here, 1.6, and then 1.2, right? Okay, we'll do it one at a time. It's a bit close to each other. This is 2.32. What does Q norm 0.9901 mean? So these are the parameters of your standard normal, or like not standard normal, but well, it is a standard normal, but these are the parameters for normal distribution, right? It doesn't always have to be 0 and 1, but when it is 0, 1, that means it's standard. What does this kind of information mean? When you have a z-score of 2.32, so the probability of z being less than or equal to 2.32, right? The probability of this happening is equal to 0.99, right? That's what you're feeding into here, right? So if you want probability of your z-score being less than or equal to a particular number, and you want that probability to be equal to 0.99, then you get 2.32 as your output, right? 99% of the data lies here, okay? In the green area. For 1.28, let's use a different color. 1.28, that means 90% of your data lies here, right? For 1.64, let's say this is 1.64. What does this mean? 95% of your data lies in this area, all right? Okay, so in this question, let's take a look at what we want. We want 0.01, so probability of my z-score being larger than. So remember that this gives you z-score less than, right? So larger than will just correspond to the other side of the graph, right? So in our case, we'll know that we want the 0.991 because the other side of that will be 0.01, right? So we can tell that our z-score in this case should be 2.32. And yeah, then we just have to solve for n minus 500 over square root 50 equals to 2.33. And then this is just simple calculation. Put in your calculator, you'll find that n is roughly equal to 537, right? And to conclude, yeah, you should say that each theater should have at least 537 seats to ensure that there's only 1% chance that too many people come into one lecture theatre, right? Okay. Next part is the delta method. What is the delta method? Well, let's have a look. y1, y2, blah, 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 be a sequence of random variables such that it's standard normal. Suppose that g is differentiable in the neighborhood of theta and that g dash theta does not equal to 0. What does this look like? It's basically saying, I guess like the easiest way to interpret this, I would say, is just say you have some random variable, I can apply a function to it, apply a function to this random variable, and after I apply the function to this variable, there'll be like a new distribution that looks like this, which will still follow the standard normal distribution, right? So this is very useful in modeling the distribution of functions of random variables, right? So let's say you have a function of a random variable you're interested in, and you want to know its distribution. You can start by finding out the distribution of that random variable itself first, which is probably a lot easier to find most of the time, and then you apply this concept, or like this kind of theorem, but called the delta method, and then everything just comes out nicely for you, right? Okay, we'll have a look at kind of a example. So you start off with a bunch of independent Bernoulli random variables with parameter p, and you have yn to be defined as the sample mean of the Bernoulli random variables, right? Show that as n approaches infinity, square root n times yn minus p converges in distribution to normal distribution with these parameters, right? Okay, let's take a look how this might work. So it's the mean of IID random variables, central limit theorem, just apply that again, right? Minus the mean divided by standard deviation, right? So we know that this kind of thing should approach the normal 0, 1, right? What might we want to do here? Well, we know the specific type of distribution it is, right? It's a Bernoulli distribution, so we can actually figure out the mean and the standard deviation, right? And we can just put those values in, right? Yeah, so you can read this off the table once again and sub these values in, right? And subbing these values in and just doing a little bit of rearrangement, you should get square root n times yn minus p converges in distribution to the normal 0, p, 1 minus p. How does that kind of work? How do we get from this step to kind of this step? It's just like you, so this gives you, well, this should actually be square root n of yn minus mu over standard deviation, right? If this follows n, 0, 1, remember this is your variance, right? It's a parameter for your variance. So when you multiply over, right, yn minus mu, you have to multiply by the standard deviation squared, right? So whatever it is here, this will be your standard deviation squared. And yeah, since the standard deviation is square root p1 minus p, when you multiply over, square it, so you get p times 1 minus p. Okay, so that's for the first part, right? Now the second part is actually the one we're a bit more interested in, and I do believe there is some typos for this part, probably even this part as well, but we'll go through the solution and I'll just point out where the typos are, but I'll just, you know, outline that there's probably typos here. And you'll quickly see why, right? Or actually I'm not, we'll see. There might not have been this question actually. Okay. So we can identify, yeah, so as I said before, right, what does this kind of look like to you? It should remind you of the delta method that we were discussing before, right? What does this look like? This looks like some function g of yn, right? More specifically, this function looks like gx is equal to x minus x squared, right? That's what the function looks like. Okay. Now, how do I go about doing the delta method, right? Well, let's have a think, right? First of all, you want to differentiate the function, sub in the mean, Why do we do that? Well, sub in the mean because it gives you the thing on the bottom of the delta method that you want. So remember, there's like a absolute value g dash mu on the bottom. It would be nice if we put up the delta method again. Yeah, so if we take a look at here, whenever you want to apply the delta method, you always have to remember differentiate, right? Differentiate, find out what this is, right? We take the absolute value of it, and then the rest kind of just looks like, if you can kind of see, right? This kind of just looks like the term above, right? We just have to scale it by some constant called g dash theta, right? And we can find that pretty easily. Yep. Okay. So, okay, there might not be typos in here. We'll see. We'll see. Okay. So obviously in this case, then g dash of the mean, which was known to be p, so it's going to be g dash p equals to 1 minus 2p, right? Okay. And then from the delta method, we can also just plug in what it should look like at on the top, right? So g of yn minus g of p over magnitude of g dash p times that approaches in distribution to that, right? And you see everything there is just kind of an application of what we've just done, right? It's just subbing in all the values, identifying what your function g should be. So then what does that tell me? That tells me that this distribution converges to standard normal, right? But was that the one we wanted? No, not exactly, right? This is the one we want. So it's the exact same as what we already have, but kind of you just get rid of the denominator, right? How do you get rid of the denominator? Well, I already discussed this, right? You can just multiply the denominator across, but you have to remember to square it. Right, and we'll see after multiplying the denominator across, well actually, yeah, just make sure you take the root n to the front as well. Yeah, multiplying the denominator across, so in this case, all we're really multiplying across is just this part, right? So then you get 1 minus 2p squared times p times 1 minus p. All right. Now on to estimators and the properties of estimators. Why do we want estimators? Because usually we don't know the parameters of our distribution, right? We wish to obtain some way of determining an estimate for these parameters using data that we collect, right? The very basic one is like the sample mean, right? The sample mean is an estimator for the, I guess, expected value usually. Well, like it depends on your distribution and what you're looking at, but and yeah, as you see here, estimator theta denoted by theta n with the hat on top, any real function of random variables. So these are like kind of your like observations, and using some function of these observations, you can determine some type of estimator for a quantity you want to estimate. So the hat on top just represents that that's an estimator for that quantity. Okay. Okay. So, and we want to say that if we want the estimator to be effective at doing its job, it should have a couple properties, right? Well, what are these properties? The estimator itself is a random variable, which means it should also have a probability distribution, which you can compute just from knowing the distribution of x1 all the way to xn, right? Yeah, and then obviously link everything, nearly everything from this point onwards, you can link to the central limit theorem, and in this case it just tells us that the estimator given certain conditions should be approximately normal. Okay, estimator bias, right? What is the bias of an estimator? You can kind of understand what this means, right? Like the bias of an estimator, like is this estimator does it tend to overestimate? Does it tend to underestimate? If it does either, we would say it's a biased estimator, right? Because the idea of an estimator is that it should be non-biased, right? It should be trying the best to accurately predict what the estimated quantity should be, right? So what do we do in this case to look at the bias? We look at the expected value of this estimator, right? If the expected value of the estimator is equal to the quantity we are estimating, then we can say that the bias is 0, right? Okay, let's take a look at an original example. So this did not come from any exam. Suppose that x is a discrete random variable with probability mass function p of x. Then you suppose that the space of x is finite, right? Suppose that x1 all the way to xn are samples taken from this x, such that each sample is independent. So these are all IID. Prove that this estimator is an unbiased estimator, and you want to compute the variance of the estimator, right? Okay, let's have a look, right? So to find the bias, we need to figure out the expected value of the estimator, right? And then, as you'll see, the expected value of the estimator is 1 over n times it's just pretty much subbing in the expression for the estimator inside. We can pull out the 1 over n, and we can just sum up all the expectations separately, right? That's just kind of like a, property of the expectation, right? Because we know that they're independently distributed. Okay, we want to figure out the distribution of the indicator function, right? But the indicator function, all it really does is just assign 1 or assign 0, right? Indicator function should have a Bernoulli distribution, right? Okay, then let's look at a particular case, right? So the expected value of the indicator function of xi, right? So that's the probability that xi is going to be equal to aj. And so we just kind of have these sort of equations, right? In the end, you just sum up p aj n times, and you divide that by 1 over n, so that's equal to p of aj, right? Not too difficult here. So then we can see that this will be an unbiased estimator. Okay, now what do we do? Let's look at the variance, right? So if we take a Bernoulli variable, we know that the variance is going to be p times 1 minus p, right? And then the variance of this estimator is kind of same thing as before, just shoving in the expression for the estimator. We take out 1 over n, but remember when you take out something out of the variance, it gets squared. So that's going to be equal to 1 over n squared, and then you can take the variance of each of them separately. And each of them separately is going to be equal to paj times 1 minus paj. Sum that up n times, divide by n squared, so it's going to be paj times 1 minus paj, all divided by n, right? Okay. Now, estimator variance. The estimator is a random variable, so it also has a variance, right? We want the variance to be small, since then it would be whatever value it produces, we'll know that it is reliable, right? What is the standard error? Well, the standard error is just the square root of the variance, okay? Not too hard to understand this. Okay, so now we take a look at the mean squared error. What is the mean squared error? The mean squared error is just defined as the expected value of your kind of estimator minus your mean squared, right? Kind of looks like the variance, but not quite. And you'll see that below, the mean squared error is actually equal to the bias of this variable squared plus the variance of that variable, right? Okay. And now, when we're comparing two estimators, the mean squared error is useful, right? Because it combines bias and variance. So if MSE is minimized, we are, well, it says effectively minimizing shared contributions of bias and variance, but you can just pretend it that is just basically finding the sweet spot between lowering bias and lowering variance. Sometimes you'll find that the case is by lowering bias, you kind of increase the variance, and the other way around as well, right? But when MSE is minimized, you kind of achieve like the best of both worlds. And then, yeah, here's just like the proof for the mean squared error, right? You can take a look for a bit, but probably won't leave this up for too long. I don't think there's too much point in going through the proof. Okay, properties of estimators. So we're still on properties, and we're on to another example, right? So before I even start the example, like, I don't know if you guys seen this before, but this is just like some type of scaling factor, right? Sometimes when you come up with a proposed estimator, you'll find that it's like very close to the original, but it's off by some type of constant. Usually you can just adjust for it by like multiplying, or like adding, subtracting, whatever constant it's off by. And that's kind of the idea here, right? But we're not too concerned with that case. We're like not concerned with that in this question, because all we need to do here is just show that the estimators are unbiased, right? So the tricky part here actually is if I want to know the expected, so remember that the bias is the expected value of the estimator minus the quantity we are estimating, right? So the quantity we are estimating, we'll always know what it is, right? In this case, it's just theta, right? Trying to estimate theta. But the problem here is the expected value, right? Like, how do I find the expected value of this thing? The expected value of the second expression is much easier, but the expected value of the first expression is actually not too easy. But you can have a think, right? Usually when you want to find the expected value of something, you times like all the probabilities by x, and you either sum over, for the discrete case, you sum over all of the possible cases, or in the continuous case, you sum over the integral after you multiply by x, right? Okay, now let's have a look. Calculate the expectation of the first estimator. So, as I said, you might want to find the PDF, right? Finding the PDF is kind of hard, so we'll just start with finding the CDF first, right? How do you find the CDF? Well, think about the definition of a CDF, right? So this definition of a CDF is the probability of random variable being less than or equal to some quantity, right? In this case, let's just let this be u. So for example, I want the probability of u being less than or equal to u, where u represents the max out of these n random variables, right? If u is larger than or equal to all of these random variables, what does that mean? All of these random variables are less than or equal to u, right? So I can just take the probability of all of them being less than or equal to u and multiply that together. And we'll find that for any given random variable to be less than or equal to u, we follow a uniform distribution in this case, so we'll know that's equal to u over theta, right? Pretty self-explanatory. Then we take everything to the power of n, right? Okay, so then we know that f of u, which represents the max of these random variables, is equal to u over theta times n. So if we have the CDF, then we can find the PDF, right? Just by differentiating, not too hard. Okay, so then we go to differentiate, we find out the PDF, and then we integrate over the correct bounds, right? So to find the expected value, multiply by u, and then integrate over the respective bounds, right? And then you'll see that it should be equal to theta, and we can conclude that this is unbiased, right? The integration shouldn't be a problem, right? Steps are here as well. Okay, now the second case, right, where theta is equal to 2 times the sample mean, right? This is actually quite easy because we know the expected value of the sample mean is just the expected value of any of these variables, and the expected value of a uniformly distributed, in this case, from 0 to theta, would just be theta over 2, right? And we take 2 times that, so think about scaling by some constant, then you just get this equals to, you get, the expected value of this estimator is also equal to theta, so which means it is unbiased as well. Okay. What else did we want? I think we also wanted the mean squared error, right? So typically the mean squared error, you have to remember that's equal to bias squared plus variance. But in this case, bias is 0, so mean squared error is just equal to the variance, right? Okay. So then back to this expression, you want to calculate the variance. Did I skip something? I did. Okay, yeah. So back to this, you want to calculate the variance of 2 times the sample mean. Well, you can bring out the 2, but you have to square it, and then you take the variance of the sample mean, which we should know how to find as well, right? Now, for the other case, right, the case we were dealing with before, the variance of this thing, you pull out the constant, square it, and then you want the variance of the max of x1, x2, xn. Well, how do we do this? Well, if you kind of remember, variance is equal to expected value of u squared minus expected value of u, whole thing squared. So then, how do we find the expected value of u squared? Just multiply the expression by u squared, integrate with respect to the normal bounds, and then minus the expectation, right? The expectation we already know as well. Yeah, and then after combining like these, terms together, after integrating, combining together, we should get something like this: n over n plus 2 times n plus 1 squared times theta squared. And then, well, you might want to talk about what's the better kind of estimator, right? So you have this estimator here, which is n over n plus 2 times n plus 1 squared times theta squared. Let's have a look at the other estimator, what the variance of that was. 1 over 3n times theta squared, right? So what we are trying to do is we're trying to compare this to 1 over 3n theta squared, right? Think about which one is better. How do you know which one is better? Well, like this term is like you have a degree 1 term, which is n divided by, essentially like this will behave similar to n over n to the 3, right? So this will behave similar to 1 over n squared, whereas this just behaves similar to 1 over n, right? We know that for large values of n, 1 over n squared is going to be much smaller, right? And that's kind of what the notation suggests, right? 1 over n times n plus 2 theta squared is equal to O of the variance of that, and hence theta with the hat on instead of the tilde is the better estimator, right? Just because the variance is much smaller and they're both unbiased, right? So there's nothing to say about the bias. Okay, properties of estimators, right? What are some properties of estimators? Well, what's a interesting one, like consistency, right? Why are we interested in the consistency? Well, you want your okay, so first of all, the definition of consistency is as the limit approaches to, or a limit as n approaches to infinity, probability of this thing larger than or equal to epsilon is equal to 0, right? So as we've seen before, this is just a convergence in probability, right? Then we can apply the Chebyshev inequality, right? What does this tell us? So using Chebyshev inequality, you can say that, like to the previous part, using the Chebyshev inequality, if MSE of an estimator approaches 0, then the estimator is consistent, right? So this is a kind of important thing to keep in mind, right? So, but it doesn't really go the other way around, right? So if MSE approaches to 0, the probability also goes to 0, right? So it goes this way, but probability goes to 0 does not mean that MSE goes to 0 as well. The MSE is stronger than the probability, if you can remember. Okay, asymptotically normal. An estimator of theta is called asymptotically normal if this is the case, right? If, once again, minus the mean divided by standard error or standard deviation, but standard error works better here. They kind of mean the same thing. converges in distribution to standard normal. Okay. Parameter estimation and inference now. So we're kind of approaching towards the end of the course now. Okay. So we've dealt with all of that. Now we want to deal with the maximum likelihood estimator, right? Short form MLE. What is this thing? Well, for example, if you take x1 all the way to xn observations of a random variable x, right? You can compute some likelihood function, right? What does that kind of mean? The likelihood that you observed all of these different values, right? For example, what is the likelihood that I observed x1? What's the likelihood I observed x2, x3, xn, right? We usually know that these are IID, so we can just multiply the probabilities together, right? And we're saying that the maximum likelihood estimator is just an estimator that maximizes this likelihood, right? Why does this kind of matter? I guess we'll find out later, right? But let's just take that for granted for now. The log likelihood of theta is just, we just take the likelihood function and just take the log over it, right? Like the natural log usually. Why is this important? Well, it just makes differentiating easier, right? Because when you have ln and you have products of a bunch of things, ln is just nice because then it splits up products into sums, right? Okay, and also ln is an increasing function, which I guess is very important. Yeah, we talked about this. Yeah, log likelihood function is also an increasing function, so whenever you have the maximum likelihood estimator for the log likelihood function, it's the same as the maximum likelihood estimator for the normal likelihood function. Okay, so in this case, the Pareto distribution is brought up, but I'm not sure if it's still in the course anymore. But I guess if they give you the distribution, I guess it can still be assessed, right? X has a one parameter Pareto distribution. Density function of X is as follows. Alpha, which is sometimes known as the Pareto, whatever. And you want to show that the maximum likelihood estimator of alpha is this thing, right? Once again, right? If you think about multiplying all of these probabilities together, it'll give you like some really long, annoying expression, right? Alpha to the n times x1 to the power of negative alpha plus 1 times x2 to the negative alpha plus 1, and so on, right? Differentiating that is kind of a nightmare. That's why you want to take the log, right? Okay, so now if we take the log and we differentiate it, right? So first of all, you take the log likelihood function and it'll look like this, right? Alpha to the n, the log of alpha to the n, you can just take the n down, n times log alpha, and then alpha to alpha, negative alpha plus 1. So you'll have like, essentially you have x1, x2, x2 all the way to xn to the power of negative alpha plus 1. And then you can take all of that down, right? Take all of that down. And then we just differentiate as so, right? Differentiate with respect to our variable alpha. Okay, differentiate with respect to our variable alpha, what do we get? We get n over alpha, right? Minus the diff of alpha plus 1, right? Which is just 1. N over alpha minus all of the log added together, right? We know that we have the MLE when the derivative is equal to 0, right? So in other words, it happens that alpha equals to n over the log of all of these things added together, right? Why do we check the second derivative? We check the second derivative to ensure that the maximum is actually, to ensure that it is actually a maximum, right? So second derivative less than 0 means that it's a maximum. If it was equal to 0 or larger than 0, then we'd have a bit of a problem. Okay. Next, some properties of the MLE. We have the consistency, right? What is the consistency of the MLE? Okay. The consistency of the MLE, I think probably discussed this before, right? Yeah. So essentially just the estimator converges in probability to the theta, right? Equivariance, says equivariance, but I'm fairly certain that this is just the continuous mapping theorem. So essentially, if some estimator for theta is the MLE of some parameter theta, and g theta is some function of theta, then the MLE of g theta is g theta, or like g of the estimate of theta, right? And yeah, I guess they call it equivariance, but I don't think we've ever encountered that. Asymptotic normality. What does this look like? Well, just the same thing as before, right? Just minus mean divided by standard error converges to normal distribution with parameters 0 and 1. Okay, next thing, the Fisher score and Fisher information, right? So yeah, Fisher score and Fisher information are defined as so, right? A Fisher information given by x1 blah 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 xn is defined to be the expected value of the Fisher score, right? And you'll see that there's like a couple different what do you call it, expressions for it. Yeah, so you can have generally, yeah, these two expressions, and then there's the other one which involves the variance. I think the expected value of the variance of d over d theta of the so essentially it's the variance of this function of the inside. Yeah, that's the other expression you can have. All right, so this is just kind of the definition, right? The L here just means the log. Okay. All right. Okay, and yeah, so typically you write Fisher information using an I. The variance of the estimator is usually can be approximated by 1 over the Fisher score or Fisher information. And then you'll know that the standard error will just be the square root of that, which is not too bad. Okay. Let's do an example, right? x1 all the way to xn follows distribution f, where f is given by this distribution, right? X larger than or equal to 0, theta larger than 0. Let's say you want to find the estimated standard error of this estimator and the approximate distribution of this estimator if it is known that I and theta is equal to n over theta squared, right? So we know that the standard error is roughly equal to the estimator divided by square root n, right? What does that mean? Then the estimator minus the mean divided by standard deviation approaches the normal distribution, right? In other words, if you want to rearrange it, you can say that this estimator approaches in distribution to normal with parameters theta squared on n. Okay, so we have estimators, right? But since estimators are random variables, as we can see here, won't actually always equal to the actual parameter. In fact, if this thing is continuous, then the probability of it actually being equal to the quantity we're estimating will be 0, right? And to kind of solve this issue, we go to construct confidence intervals, right? So essentially, instead of giving the probability of our estimator being equal to the quantity we're trying to estimate, we instead give a range of possible values and we give like a confidence, right? So for example, I'm 95% confident that my values lie within a particular interval, right? Okay, definition of the confidence interval, right? Let's take a look, right? x1 all the way to xn is a sample on a random variable xi, where it has some particular PDF. That 0 between alpha between 1 is specified. Why is that the case? Well, if it was any larger than 1 or any less than 0, it just wouldn't make any sense, right? Okay. We say that, so L and U being lower, upper, obviously, it's a 1 minus alpha times 100% confidence interval if 1 minus alpha is equal to the probability of theta being between the lower and upper bound, right? and this is just what the confidence interval looks like, right? It's just a definition. Not too much to worry about there. Okay. If we have that this estimator is consistent and asymptotically normal estimator, then an appropriate confidence interval for this would be as follows, right? Why is that the case? Well, so essentially we want to be 1 minus alpha times 100% sure that this is the case, right? If it's between these two values, think about the distribution, right? You have your z 1 minus 1 over 2 here, and your, I guess, negative z 1 minus 1 over 2, 1 minus alpha on 2 here, right? What does that mean? Alpha over 2 of the values lie here, and alpha over 2 of the values lie here, right? So the interval that you give them will contain exactly 1 minus alpha, right? And that's the idea. How do you construct these confidence intervals? Well, you always have to start off with the estimator, right? And you want to find a distribution that we can apply the estimator to, right? In most of the cases, we'll just do to the normal distribution, right? Okay. Then we go ahead, we find the quantile values of the normal distribution, imply a 1 minus alpha confidence interval, and we'll observe this kind of thing, right? 1 minus alpha is equal to the probability of it being between these two kind of z-scores. Then we send all of the variables to the other side, and then we just get our mean between all of the variables, right? That's exactly what we want. So we take a look at this for a bit. All right. Let's see. Okay. Let's have a look at a question here. So we have 5 water samples taken from a small dam. Cadmium levels are measured, and the average of these 5 values is then used as an estimate of the cadmium concentration in the dam. Okay. The sample mean was 0.055 milligrams per liter with sample standard deviation of 0.006 milligrams per liter. Construct a 95% confidence interval for the true mean cadmium concentration in the dam, right? Okay. Let's have a look, right? If we have mu to be the true mean of concentration of cadmium, and we're given the following information, right? As we've kind of determined before, we know that the 95% confidence interval for this will be roughly as follows, right? Usually this, you should be given a table bar, otherwise you'll know that the probability of z being the z score corresponding to 0.975 is roughly equal to 1.96. And then you just apply formula to it, right? It's not too bad. Yeah, and then just the rest of that is just throwing in your values. All right. Hypothesis testing now. Yep.
How do you rub out with the pen?
It's like a...
Just checking, just so.
Should be this.
You switch to that, so you just go.
Or you can double tap it.
You just go that.
You should be able to double tap it, yeah.
Okay.
Double tap to switch.
Right, like this, like that. Just that.
Just tap the pen twice.
Oh, really? Something like that.
Okay, no, wait. Okay, but like sometimes you can just like squiggle over it.
At the least, I can always just do that.
I mean, you have to like make it like kind of obvious.
Okay. Thank you. All right. So the last topic that we're going to be going through is hypothesis testing, and that's really bringing together a lot of the content that we've just done in this lesson when it comes to hypothesis testing and the MLE and these estimators and these standard error estimates. So we're just going to get started here. So firstly, what actually are we doing when we do hypothesis testing? So some of the key definitions that we want to look at are the null hypothesis, which is normally labeled as H0. And that essentially is a claim of saying that some parameter of us takes a particular value. So we normally think about the null distribution when we're doing a hypothesis test as, okay, has there been a change like after we've done an experiment, or is there an actual effective change? But the null hypothesis, essentially, there has been no change. It actually just is represented by this basically null distribution. Secondly, we now consider the alternative hypothesis. You see it labeled as HA as well. And that essentially is a much more general hypothesis about the parameter of interest. And key to our hypothesis test, we will consider this to be true if we believe there's enough evidence against the null hypothesis that we're actually able to reject it. So the two kind of main things we think about is, are we able to actually reject the null hypothesis, and how much evidence is that going to require? So you can see here that we normally have sort of three hypothesis tests. So the first one is going to be your two-sided, and these other two at the bottom are going to be your one-sided. So that will depending on whether it's a two-sided or one-sided test, that will definitely change the distribution that we're going to use. So, and you can see here sort of a reiteration of what I was saying before, is that we're going to use our data to actually test H0, and through those distributions we're about to use, we're going to actually see how much evidence does our data offer in favor of H1 versus H0. So this is basically sort of a few basic steps on how you actually want to conduct a hypothesis test. So firstly, it's always key to actually state what is the null hypothesis and the alternative hypothesis. That's always going to be your first step. We then use our data that we've gathered to actually answer this question that I've been talking on about, which is how much evidence is there against the null hypothesis. So in doing that, we want to actually find a test statistic which measures how far our observed values will actually differ from what we expect in the null hypothesis. So depending on the underlying distributions, whether we're estimating parameters, very common ones obviously is your normal distribution. You may see a t distribution, and there are also potentially other distributions that we may use. Those are definitely the two most common. Secondly, we then use those distributions to help us calculate the p-value at those points. So sort of very, very similar to confidence intervals. It's basically the probability of observing a test statistic that is just as extreme as the actual observed value, if indeed the null hypothesis is true. I mean, in basic terms, essentially all that's saying is that if our p-value was 5%, we'd expect that if the null hypothesis was true, 5% of the time, we would expect our observations to be within that far away from our null hypothesis mean. So essentially, we're basically going to consider whether what significance value do we want to take that we consider enough evidence. 5% is very common, but that's effectively what that's saying. And then we use 2.2 to then say, let's say we chose a 5% significance level, and then let's say we found out our p-value was 4%. Okay, so because our p-value is less than our significance level, we would then say, okay, we have enough evidence to reject the null hypothesis. However, let's say our p-value is 10% and our significance value that we were taking is 5%. We would say not that the null hypothesis, not that the alternative hypothesis is not true. We would just basically say we are unable to reject the null hypothesis in that case. Okay, so this is basically a short example of how we can actually apply basically what we've done before. So here we're basically taking John, and he's gone up to the line on the free throw, and he's testing his free throw percentage. So in 24 attempts, John manages to make 14 free throws. So now we're going to consider, is this evidence that John is there enough evidence that we can consider John basically a better than average, which we're going to assume is a 50% shooter from the line? All right, so first of all, we're just going to assume in this case that's a binomial distribution. A binomial distribution. So that basically there's two outcomes, and basically they have a probability P and 1 minus P. So in this case, that's the assumption that we're making here. We're basically, P is obviously equal to when John makes a free throw, and the alternative, or our complement, is going to be John doesn't make the free throw. So first of all, we want to consider, okay, what's our test statistic going to be? And essentially, I'm doing more of a shorthand that you guys might have seen, where we can actually consider a normal approximation as appropriate if our number of trials times our probability is greater than or equal to 10, and the number of trials times basically our 1 minus our probability is also greater than 10. So, and this is specific to a binomial distribution. I'm pretty sure that 1 minus P, I'm pretty sure that would change, because I think that's referring to more of a standard deviation. So if there's a different distribution, that would be different, but this is basically a shorthand. Okay, is the normal distribution like appropriate in this case? So in this case, both are 12, which are greater than 10, so it is appropriate. So here, now we have a look at, okay, what's our null? Our null hypothesis is that he is just a 50% shooter, right? So he got lucky in making those 14 or above average. And then here we can see that H1 is the probability that he is better than average. And you can see here specifically, we're referring to a one-sided tail test here, not a two-sided. So we don't consider whether he's less than the 50% shooter. We're considering whether he's better, so just greater than that half. Okay, so now we kind of move on, to developing our approximation here. So you can see here, very similar to what we've just covered, we take our estimated parameter, we take our sort of mean value here, or our basically null value of a half, and then here you can see this is simply just our, this is simply just going to be our standard deviation on root n. And so all we're doing is we're just doing that very simple thing where we're just going that parameter minus mu all on that SE, and that's approximately going to be n01. So very similar to what we've just done before. And now we can just simply plug in all those values. We know that P is just going to be 0.5 here. All right. So now we're again moving to sort of that step 2. So how much evidence do we have that making 14 out of 24 allows us to say that he is a better than average shooter? So it's a very unlikely to have happened by chance. So we're basically considering, okay, what is the proportion, if we were to consider null hypothesis, what is the proportion? So just imagining here. So, and let's just say we had 14 there. What percentage is this area here? And let's say, and depending on our significance level, we're going to take 5%. If this is less than 5%, then we can say there is enough evidence to actually reject the null hypothesis. So here, you can see all we've done here is we're basically just divided that by our null hypothesis or our mean. And all we do is we essentially can just, here, this is basically just plugging everything in there. And then we end up finding that we're looking for P, Z is greater than 0.82. And obviously this is where you would get some values, and hopefully that if you see Z082 is equal to about 0.20, that's very good, because that means you probably found the right Z value. So obviously this is more your calculation side here. But if you do see this as sort of a given value, you know you're on the right track. And we can see here that we end up with P, Z is greater than 0.82 is approximately about 20%. So I'll see here if we make the conclusion. But essentially all our conclusion is going to be is essentially if we found that, so we have let's take a 5% significance level. All we're saying here is that, okay, because our p-value is sort of greater than that 5%, we would say not enough evidence to reject the null hypothesis. Yeah, so basically that's, you just want to make sure you make that conclusion, just to be, okay, do we reject it or do we accept, or do we not have enough evidence to reject? So now we're sort of moving on to, okay, well, this is level of significance. We consider some level of significance alpha as a threshold at which we reject the null hypothesis if p is greater than or equal to, p is less than alpha. And very common one that we use is obviously 5%, but you may also see 10% and 1%. And you can see here we've sort of made that conclusion for 0.3. And this obviously says we accept the null hypothesis. I would probably phrase it as how I did before, that we have not enough evidence to reject the null hypothesis. Because again, if you remember science, hypothesis, we're basically always, the whole thing about forming a hypothesis is you're trying to reject it in science. So the whole idea in statistics is a very similar thing, where we're actually just trying to find enough evidence in that we can, in our level of significance, actually reject it. So we either reject the null hypothesis, or where we don't have enough evidence to reject the null hypothesis. So in this case, I would have said something like this, where we have not enough evidence. All right. So now we're sort of moving on to these test statistics, because this is probably one of the more important bits, like which test statistic are we actually able to use? So now we're going to consider, okay, we have some set of random variables, and they're all basically normally distributed. Now we can use that fact that we discovered before, that if we here we're estimating S in this case, which is important. If we weren't estimating S, we can easily just use our normal distribution. So this was some sigma known, and you can see I've made that note. We can just use a normal distribution. But in the case where we're estimating our standard deviation, here we would actually use our student t distribution with our n-1 basically degrees of freedom. And you can see here we would use that for all of our two-sided and our one-sided tests. Okay, so now we're going to kind of move on to the example related to that. Okay, so we can just read here, and you can see here there's a lot of information actually related to the question. But importantly, we want to find what's our mean, what's our standard deviation, what's our number of observations, are they normally distributed, like what's our distribution underlying it, because then that kind of tells us. So we're kind of looking for like a mu, potentially standard deviation, maybe we have to calculate it. Basically number of observations. And we're also looking, okay, like what is our underlying distribution for the random variables, not for our hypothesis test distribution. So that's what we're looking for. So here we had mu is 900 tons. We have n is equal to 50. We have our sample mean is going to be 910. And our standard deviation is S is equal to 25. And you can see here again, so these are all of our key considerations here that we're going to want to use. So we're assuming our yield is approximately normal. So then because our standard deviation has been like estimated, we're able to use that student t distribution as above. So here, and also importantly, actually another consideration is we actually care, are we considering a two-sided or a one-sided test? In this case, this is what we look for. We only care about if it's more efficient, not if there's been any change. More efficient only means, hey, we only consider it's better than 900. So we're only considering a one-sided test there. So here you can see we've written that as our null is going to be 900, and our alternative is that, okay, it is more efficient, it's greater than 900. Here again, because it's normal and we're estimating our standard dev, we can actually use our student t distribution here. And then so once you've found all these values and you know the correct distribution, it's literally just a fact of plugging everything in. So that's why it's really important. Like once you know which distribution the underlying variables are, and which one you can, and from that, which one you can actually use. It's really easy because all you're doing is just plugging everything in here. So you can see here, all I've done is just plugged everything in, and we end up finding PT is greater than 2.83. Importantly, obviously, n minus 1 degrees of freedom. So because of 50 observations, we have a T49 distribution. So using R, in this case, of course, this would be given to you in the exam. We would actually find that the probability that this is true is going to be 0.3%, which actually, I think that should be 3% actually. It should be written like this. So here, so I think this is written as 3%. If not, obviously, you guys can tell me that is wrong. So question mark here, if that value is correct. This 2.83 should be fine. So because what is actually saying, again, moving to 0.3, can we reject it or not reject it? Basically, it's telling us if H0 was true, we would be highly unlikely to observe a test statistic as large as 2.83. Because our value of 3% that we found, our p-value, is less than our significance value, we're able to reject the null hypothesis. And because of that, we're able to say there is enough evidence so we can actually conclude the machinery is more efficient. So you can see here, another way that we could have solved this is by rejection, basically boxes. So in this case, because we're considering a 5% significance level, we would consider the area, and also one-sided test, we would consider the area, imagine drawing a distribution. Obviously, this is a student T distribution. Let's just say this is at, this is 5% of area here. We basically, okay, what's the corresponding T value here? Corresponding T value is 1.68. Because our T is greater than 2.83, because that 2.83 is greater than 1.68, we know it lies within this sort of box here. And because it lies in that box, we can then conclude that, hey, we actually are able to reject the null hypothesis here. And I think another way that you can also do it is through like a power distribution as well. I'm not going to go into that, but because this sort of method is really good, and also very similarly, a rejection region is also very similar. Okay, so now we're going to move on to some tests. So we're going to start off with the Wald test. So the Wald test, so you can see here we've been considering a lot of one-sided tests. We haven't considered any two-sided tests so far. So here you can see here with the Wald test, we're actually considering a two-sided test. So that's going to actually allow us to now test these two-sided, basically hypothesis tests. And then you can see here, this is very similar to what we were talking about before. When we're talking about, hey, it's basically our parameter minus that null distribution all divided by that standard error. And that is going to be approximately our normal, basically scaled down to 0, 1. So here, for our step 2, all we want to do is substitute basically our null parameter to find our observation. So very similar when we plugged it in, and then hopefully here, you can see our p-value is a little bit different. Okay, then why is it different here? Why is there that 2 there? The reason that 2 is there is because now we're not considering just one side of the distribution, but we're considering 2 sides. So here, so if our p-value that we find is, so let's say if our z greater than y obs, so let's say our y obs is 1.6. So here, potentially, let's just say this is 1.6. Potentially, it's because of the symmetric properties of these distributions, or the normal, potentially we could lie either in that region, either in our lower region here, or we could lie in our higher region here. So pretend there's that 2s, and because of the symmetric properties, this area here is basically the same area. So we're able to just, if we can literally just consider the y obs is greater than 1.6 and then just multiply that by 2. So that basically gives us our resulting p-value because it could lie in both of those. And very similar, if our p-value is less than our significance value, we're able to have enough evidence to reject that null hypothesis. Yeah, and just an aside, obviously there's some other distributions that we can use. Very common one with Wilson. I think, what's the other one called? It's like Augusto-Cool distribution. I don't know if it's been covered in 2801, but I just wanted to make it as more of a side here. Essentially, Wilson's better, more accurate, but like very complicated. And then Augusto-Cool is sort of basically less accurate than Wilson, but more accurate than Wald. But it's think of Augusto-Cool as more like a compromise between the two, because Wald is very simple but not very accurate when it comes to like close parameters between 0 and 1. Wilson's very accurate but it's more complex. Augusto-Cool is basically a compromise between the two. So now we're going to move on to another test that we can use, which is a likelihood ratio test. And for the likelihood ratio test, so what the function that we use is our chi-square. And obviously you guys have seen chi-square before, but just a reminder, it is the distribution of the sum of squares of basically k independent. Just put n, z squared, obviously where our z is our standard normal. And here, this has been given, our probability density function of our chi-squared has been given here. You definitely would not need to like remember this in the exam. This will be given to you. And you can see here, something that would probably be nice to know is that our mean is basically k, and our variance is just twice that, 2k, for our chi-square. Okay, so how are we going to use that to help us? So now again, we're considering another two-sided test. So obviously this is why it's very important to consider whether it's a one-sided or a two-sided. And now our test statistic here is basically measuring, okay, I'm just going to skip this part, but essentially we just care about this part. So remember, this is L beta, it's just our log likelihood here. So what it's doing is, okay, we're taking 2. Again, that 2 is just coming from those two sides of our test that we have to consider. And we're considering, okay, what's the difference of the log likelihood of our inputting our parameter versus our just our null value. And you can kind of see intuitively, we would expect if this value here is much greater than our 0 here, right? So it's much further away from what we expect our null distribution. This will give us a very large test statistic, and we should expect that to probably be a lot less likely to actually be a part of our null hypothesis, that there actually is a lot more evidence here that we can help us to reject the null hypothesis. Okay, so we're going to go basically on the question to sort of take us through how do I actually do this. So, all right, so we're going to consider a random sample. So that, again, straight away tells me, okay, 100 observations here. We have this function here, which looks very much like a MLE would help us here. So we're going to consider these two tests here. And you can see straight away that not equals means it's a two-sided test. So we should be thinking, okay, likelihood test statistic, or thinking like a Wald interval, which they've told us to do anyway, but potentially they might not tell you, and if they don't, then that's what you should be thinking about. Okay, so they've told us what xi squareds are, and they've told us that using the MLE method, we end up finding that our parameter is going to be n divided by the sum of those xi squared. So that's going to help us a lot, because especially when finding the standard error, that is going to involve that parameter. So let's move on to how to do it using Wald. Okay, so here all I've done, first of all right, so we know it's n on our sum of xi squared, which is simply just 100, 14.81. So this is all given to us. And then you can see here, okay, that should be I theta. That should be the Fisher information there, not times n. So as you can remember, we literally just covered that the standard error estimate for a maximum likelihood estimator is just going to be 1 on the square root of our Fisher. And of course, the Fisher, we've already given what the Fisher information is before. So it's simply just minus E delta squared, delta theta squared. So you simply just, the second derivative, take the expectation and take the minus there. And without calculating here, you're going to find that this value should be like that here. And therefore, if we plug that into our standard error, very simply, we're just going to get root n. Okay, so now we're going to move on with our world statistic. So you remember, our world statistic looks like this. Standard error. And we know that's approximately about N01. Okay, so we're going to, obviously we'll leave this here, theta 0, and then we know that we're going to have, for our standard error, is going to be our parameter on root n, which can just rewrite it as root n. Like that. So that gives us actually, so we know from our, in the prior chapters, that this is actually approximately equal to our normal distribution, our standardized. And then inputting these values, all we're just doing is y-obs, it's just going to be root 100, which is 10. We already calculated that. Our parameter is 7.1336 minus 6 on 7.1336. And I put that in the calculator and I got 1.589. So now we're considering, again, that's our y-obs. We're considering this area here. Okay. And you can remember our p-value is just going to be 2 times that sort of area to the right of our curve, because we're considering the area to the left of our curve. And you can see here, I've just put in some R code for any of you that are interested. And we end up finding that our p-value is actually 11.2%. And again, usually take a 5% significance value if it's not stated, but if it is stated, potentially might be a 1% significance value. But obviously in both of these cases, because our p-value is larger than that significance value, we can't say we have enough evidence to reject our null hypothesis. So that's kind of how you do WALD. So if you kind of remember, obviously the standard error for this, for our MLE is 1 on the square root of Fisher, then I think it'd be, because usually they'll give you Fisher in these questions, obviously maybe it's a multi-part question. If you remember that, all you're doing again is just plugging in values. Or potentially you could remember as well that it's simply going to be, that obviously depends on if you get this sort of exact function distribution here. So I would rather remember sort of this value here, because usually I give you the Fisher and you can just plug everything in from there. Okay, so now we're going to move on to likelihood testing. So here I've sort of done the log likelihood. I'm sure you guys are very good at doing this, finding the log likelihood by now. So I've kind of already written that out. Obviously, if you want to have a go at doing that first, please have a go. But this is what I found is the log likelihood. So, and you can remember, now we're going to consider our likelihood test statistic. So you remember that was 2. Like this. So here, you might be wondering, okay, this part obviously relates to here. This part obviously relates to here. What happened to these two bits? And the thing is all we're doing is basically these sort of parameter values here are our inputs. And so what that actually means is that these values here, so a bit of clarity, these values here are just simply constants. So obviously we're subtracting one thing from another and both of them remain the same. They're just going to disappear. So that's why that's why it's sort of been written like this here. And again, once you know this, all it is just plugging it in. So essentially it's going to be 2 n log theta. And this is just obviously theta sum xi squared, which again is all being given to us. The 7.1337 is our MLE estimator, and that 6 obviously, if you remember, that was our null assumption. And if you plug everything in, you'll end up finding that this is actually 2.687. Okay. So you kind of probably wondered, all right, earlier, like when we were talking about these likelihood tests, like why did we randomly just bring something up about chi squared? Because like how is that related? And this is actually where chi squared comes in. Because specifically for a two-sided test, we consider the actual underlying distribution that we're going to consider this hypothesis test over is simply, chi squared of 1 degree of freedom here. Because that 1 degree of freedom basically is saying that, hey, we're estimating MLE, so that basically is 1 degree of freedom more than our null hypothesis. And then for some significance value 0.05, this again will be given to you, but our chi squared, let's put here 1, 0.05 is basically about 3.841. And again, we look at, okay, our value here is 2.687. 2.687 is less than that 3.841, so it's not within our, so this, if we imagine 3.841 is here, it's not within this area that we're able to actually reject the null. And because of that, we're unable to reject the null hypothesis. Okay. That's everything, guys. Thanks so much for coming to, thanks for if obviously you came in person or if you're watching online. And hopefully this was a lot of value to you guys, and I hope everyone does, takes this away and does really well in their final exam. So thanks for joining us, guys. There we go.